Okay, so this is day 2 of parametrics. Now, this first page is honestly more of us getting used to graphing parametrics. The next page is more about applications of parametrics. We're probably only going to have time to do this number 1 here, then number 2, and this number 1 on the last page of these notes. That is what we're going to cover on day 3, Thursday. So we honestly are only having 2 pages of notes. This first page we have to do by hand. We can't actually use Desmos or a graphing calculator because the graphing calculator automatically uses decimals for time instead of pi in terms of pi. So we are going to have to do this by hand, which is not a big deal if we remember the unit circle. So yes, the unit circle is resurfacing. We are taking these 2 parametric equations right here, and we are creating first the table and then the graph for these parametric equations. Now, we're trying to find the y value and x value for all of these points, considering the time period is in terms of pi. So, the easiest way to go about this is in your head to think about a unit circle, because we know that the unit circle will give us the sine and cosine values for each one of these pi values, for each one of these angles. You should think of them as. We know that on the unit circle, it has a radius of 1. So if I'm thinking about this first point right here, that coordinate point is 1, 0. And for a coordinate point, what does the x value tell us on the unit circle? Oh, Jack. It's so tempting because you always think in terms of sine, cosine, like sine comes first. But the x value is actually cosine of our angle, which this angle right here is our 0 degree angle. And this is the sine of 0. So, for this first value, which is 0, I'm plugging in 0 for t. We have to ask ourselves, what is the cosine of 0? And we can get the answer thinking about our unit circle. What is the cosine of 0? Yes, 1, right? Because that is the x value at that point. So the cosine of 0 is 1. I need to take that 1, this is 1, and multiply it by 2. So my x value is 1 times 2, or 2. We do the same thing for the y value. We take 0 and plug it in for t. What is the sine of 0? Again, it's easiest to think about the unit circle. What is the y value of the 0 degree angle? The y value of the 0 degree angle is 0. So 2 times 0 gives us 0. Now we're looking at the next point, which is pi. That is our 90 degree angle up here. This coordinate point is 0, 1. So the sine and cosine values have now flipped. So now we're plugging in pi over 2 for t. So we're asking ourselves, what is the cosine value at pi over t? I'm sorry, pi over 2. What is the cosine value? Zero. So 0 times 2 gives us 0. What is the sine value of pi over 2? 1. So we multiply 2 times 1 and we get 2. Now we're moving on to the 180, the pi angle, which is this point right here. This coordinate point is -1, 0. So what is the cosine at that angle? -1. So you multiply -1 times 2 and you get -2. What is the sine value of that angle? 0. So 2 times 0 is 0. You guys are getting it. Then 3 pi over 2 is this 270-degree angle, which is 0, -1. What is our cosine value at that angle? 0. So our cosine, our x value is 0 as well. And what is our sine value for that angle? -1. So -1 times 2 is -2. And lastly, our 2 pi angle is actually the same angle as what? 0. So we can just copy down that starting point. This is our starting point, and this is our stopping point. And it wants us to sketch this 2, 0, 0, 2, -2, 0, and 0, -2. What'd I do? Why did that disappear on me? Interesting. Okay. It also, most times, it doesn't say it here, but most times it'll want us to give a direction to the parametric. So we started graphing at 2, 0. That's where we started. This is also where we stopped. But we went counterclockwise around this circle. So just somewhere on the circle, give a little arrow for what direction we were graphing in. It doesn't tell you to do that here, I don't think, but most times it will. It'll say give a start, give a stop, and give a direction. And then also just super quickly, for what portion of t gives us the first quadrant? What t values give us the first quadrant of this circle? Yeah, the t values are positive. We want just this first quadrant. What t values gave us that first quadrant? Yes, 0 to the 90-degree angle pi over 2. What about the portion above the x-axis? What t values gave us those? Oh, I think it was, yeah. Yep, 0 to pi. And lastly, the portion to the left of the y-axis. Yes, pi over 2 to 3 pi over 2. This is honestly just trying to get you used to graphing when the parametrics include sine and cosine, and also get you used to recognizing what t values produce what. All right, so because we're trying to finish this kind of quickly, I'm actually going to skip part B. The only difference between, not all of part B, I'm going to skip number 2. I'm going to do number 3. But the only difference between 2 and number 1 is that it doesn't create a full circle, actually. You see how it only goes from 0 to 3 pi over 2? This means that this is not a full circle when we find these values. It's just 3/4 of a circle. This is our start. This is our stop. Our start is 0, 4. Our stop is 4, 0. We find all of the points the exact same way that we found them before. Oh, there is a misprint here. This is supposed to be a 4. There's supposed to be a 4 in front of that cosine. But the points end up being this. Again, we find them the exact same way that we did on the previous problem. by thinking about the unit circle and what the sine and cosine values are for those points. Okay. Oh, also give a direction. So actually I did end up doing number 2, but we didn't actually end up doing it. So number 3, we're going to go ahead and actually do this one. Again, we're thinking about the unit circle to help us find these sine and cosine values. So what is our x value for the 0 degree angle? Yes, 3. Because remember, at the 0 degree angle, our point is, 1, 0. So I multiply that 1 by this 3 and I get 3. What is our y value? 0. Good. At the 90 degree angle, the point on the unit circle is 0, 1. So what is our x value? 0. What's our y value? 2. Good. We're getting it. What pi has -1, 0. So what is our x value? -3. Good. And what's our y value? Wonderful. On our unit circle, our 3 pi over 2 has the point 0, -1. So what is our x value? 0. And what's our y value? Yes, you guys get it. And then remember, 2 pi is the same as 0. So what's my coordinate point? 3, 0. Good. Our start is the initial point with a time of 0, so 3, 0. And our stopping point is the last time they give us, which gives us the point 3, 0. Then we're going to graph this very quickly. We have 3, 0. We have 0, 2. So this time, this produced an ellipse, which is fine. The only thing is I'm really crappy at drawing ellipses. I don't know why. Oh my God. We're going to go with it. So it wants us to label the start and stop and also give a direction. We went counterclockwise again. Now, I answered this next question. It says the path of the curve goes, and I just told you, counterclockwise. Now here's the higher level question. How can this set of equations be changed so that the curve's direction is reversed, but still start and stop at the same point? I'll be impressed. Last period, kind of got it on their own, but I really had to help them. So I'll give you a minute or so to think about how we could change these equations so that it's still the same ellipse, but the direction is opposite and we start and stop at the same point. Yes, so you keep the same x equation, 3 cosine t, because this will produce still the same starting and stopping point of 3, 0, 3, 0. But if we make this y equation -2 sine t, this will make this point be 0, -2, and this point be 0, 2. So that would make our starting point be 3, 0, but then we would be going to 0, -2, going to -3, 0, and going to 0, 2. Exactly what we wanted to happen. We wanted to go the opposite direction, but still have the same shape. So that's an interesting concept to have. I think that Math Excel might ask you that, how to change direction. Most often it's just you negating one of the x or y values. Okay, so now on to the meat of parametrics, the word problems. Today we're only going to be going over one word problem. Next class we'll be going over another circular motion And we'll also be going over projectile motion and vertical or horizontal motion. But today, we're honestly just going over a path of circular motion. So if you look, we do have equations we're going to have to know. Why is this my new physics class? I know. Physics and math, I mean, honestly, to be honest, I don't know why they're separate in most cases. Like, I guess it's just you need more practice doing the bare math in order to truly understand how to do the physics. Advanced physics is literally just math. Exactly, yeah. So I'm sorry that things overlap, but I mean, math and physics is math, math is physics. But, okay, ignore me. Let's move on. We need to know these equations. We don't, you would have to memorize them, or would you have to memorize them if we were in school? I'm not too sure. I think that we would still give them to you, but lucky enough for you guys, we do always have this paper in front of us. Anytime we're dealing with circular motion and they want us to write parametric equations for circular motion, we're going to use this equation for the x parametric and this equation for the y parametric. Now in this case, circular motion is actually more complex than elliptical motion because circular motion deals with velocity. So here, most times we're honestly going to have to solve for velocity because circular motion parametric equations only deal with radians per second.
I just came to...
So parametrics for circles always want the velocity to be in terms of radians per second. So if our velocity is not already in terms of radians per second, we're going to have to convert it to radians per second. Okay. So here, this one equation we're doing, this one problem we're doing, and then we'll be done for today. A stone is stuck in the tread of a Hummer tire, 17-inch radius, that has a 17-inch radius, which is traveling 400 revolutions per minute. This is a velocity. Approximately 40 miles per hour. Speed is velocity. A sketch of the tire is shown below. And first it's asking, what is the ordered pair for the center of the circle? What do you guys think the ordered pair is for the center of this tire? Closest method. It actually is giving the radius. You would be correct if they had given the diameter. Yeah, you're right. The center is 17 because the x value of this circle is 17 and the y value is also 17. So our ordered pair for the center is 17. Write a rectangular equation that models the stone path. I thought it was diameter, right? So this is also, why does it keep doing this? Okay. So also, when we're doing rectangular equations, this is really straightforward. This is what we learned when we were doing conics. We take the center, the h value and k value, and subtract them from our x and y. So the h value of the center is 17, the k value of the center is 17, equal to the radius squared. Our radius is 17. So that's easy peasy to create. If only they wanted it just as a rectangular equation, we would be done. But because there is time associated to this situation, we also are being asked to form parametric equations. Now we do need to use these formulas that they have written above for us to create these parametric equations. What do we need to solve for before we can finalize these parametrics? We have the radius at 17, so we can start this, right? 17 times the cosine of, what's wrong with our velocity? Right. Our velocity is given in terms of revolutions per minute. We need it to be in radians per second. So way back when we learned about converting, this is one of the applications. We need to take 400 revolutions per 1 minute and convert this into, we're trying to get to radians per second. So if you remember way back when, I can't remember if it was last semester or not, but when we had all of those conversion fractions, we have to do the same thing here. What would you like me to do first? We have to get the numerator to be radians and the denominator to be seconds. Oh, Isaac's doing the harder one first. Yeah, I honestly, what I did when I was keying this, I always go for the easiest one first. So I did minutes to seconds, which it doesn't matter which one you do first. It does not matter. But I'm going to go ahead and do the easier one first. I know I'm trying to go from minutes to seconds. So I need the minutes to be diagonal from our existing minutes so that it will cancel out. So I need my minutes to be up top and my seconds to be on the bottom, which makes sense because my seconds needs to be on the bottom. Now, for every 1 minute, how many seconds do we? Oh, you already said it, Karina. Thank you. You guys are like, hurry up. Okay, so the minutes will cancel. Now, like Isaac said, I need to think about how to get this in terms of radians. I have an existing revolution. I need to go from revolution to radian. So what I'm asking is, how many radians, that's what needs to be up top, per 1 revolution, which we know a revolution is 1 time around a circle. How many radians are there for 1 revolution? Yes, Isaac already said it, Elise says it, Serena says it, exactly. There are always 2 pi radians per 1 revolution around a circle. So then we check, do the things that I wanted to cancel, minutes canceled, revolutions canceled. I'm left with radians over seconds, which is exactly what I needed. And now all I need to do is multiply 400 times 2 pi is 800 pi over 60. This simplifies down to 40 pi over 3 radians per second. This is our velocity. It's our only velocity, so I'm not quite sure why they're putting VO. Like VO usually stands for initial velocity. It's our only velocity, so why? Don't ask me. Okay, so now let's go ahead and put that into our equation. We had the radius times cosine. Now this is, I really have to zoom out so we can see the formula. So we had radius times cosine of our velocity, which is 40 pi over 3 times time, plus h, which our h value is 17. Then we do the same thing for our y parametric. Our radius is 17. This time times sine of our velocity, which is 40 pi over 3 times time, plus our k value, which is also 17. So those are our 2 parametric equations. Any questions on finding those parametrics? Okay, so the next thing it asks is this for us to plot the stone on the graph at a time of 0. So we could do this mentally or algebraically by plugging in 0 for t, but with this 40 pi over 3 times I guess we could easily do this mentally. But if we just aren't wanting to do this mentally, we could easily do it, turns out, mentally. But our brains are fried, so let's go ahead and just use our calculator. I was going to show you how to do this in Desmos, However, Desmos, it's impossible to find this F answer using Desmos. So if you don't have access to a graphing calculator, I highly recommend that you download WAVA-EMU onto your school laptops. Someone else was saying that your school laptops actually let you do that. If you are able to do that onto your Chromebooks, let me know. Because Desmos does fail to help you solve for part F. It does everything else just fine. Desmos does all of this just fine, except for when you're trying to find a specific T. It's impossible to do in Desmos. I don't know why. So I'm going to show you using the graphing calculator. Also at the end, if you want to stay on to see me do it using Desmos, you can, but I highly recommend you try to find a way to get a graphing calculator, either with an emulator like I have or an actual graphing calculator. Okay, so I typed these into, remember, our mode needs to be in radians, and we also need to be in parametrics in order for this to work. And then it also tells us so nicely what our window should be. Now what this means, what these intervals mean here, the first number is always our min value, the second number is our max value, and the third number is called the step or the scale. So if I go to my window, I should have 0 as my min, 0.15 as my max, and 0.001 as my scale or step, which I do. And then same thing for the x and y values. My min is 0, my max is 60, and my scale is 5. My min is -5, my max is 40, and my scale is 5, or my step is 5. And then I go in and I can see my graph. Now, I'm trying to figure out where the stone will be at time 0. There's two ways you can do this. Either you can hit second trace and calc the value of t equals 0, or you can just look at the table because this is a whole number value of t. And just find, and just find when t is 0 what your coordinate point is. It's 34, 17. So we could have done this mentally because we know if we're plugging in t as 0, that means we're finding the cosine of 0, which is 1 times 17. 17 plus 17 is 34. And then the sine of 0 is 0, so this y value would just be 17. What equation did you put into y equals? Into y equals, I put this one in for x, x1, and this one in for y1. I had just done it in the previous class, so I didn't bother doing it because it takes me a long time on this emulator to do it. But you just type in what we had found the parametric equations to be. Then it wants us to know, or it wants us to find out, at time equals 0.06, what is the ordered pair for the stone? If we're looking at our table, it does not give us decimal inputs for t. So what you have to do is you have to hit second calc to calculate the value of t when it's 0.06. And you get 3.247, 26.992. Again, all you did was hit second trace value t equals 0.06. So again, all I did was hit second trace value 0.06, enter. Now here comes the kind of messy part. We need to figure out when the stone touches the road. At what time does this happen? So when the stone touches the road, that's down here. Oh, it wanted us to also plot the starting point. 3417 is here. That's our start. But we're trying to figure out when the stone touches the road. This point is going to have a y value of 0, right? It's the road, meaning we don't have a y height. We're on the ground. And we need to figure out at what time this is happening. The only way to do this on a graphing calculator is by tracing around our parametric. Now, also, you'll notice on parametrics that the arrow keys don't work like you think they do. You actually have to go to the right to keep going and to hit the x-axis intersection. So I'm just going to spam the right arrow till I'm about on the ground. And what you're looking for is the closest y value to 0 or the closest x value to 17, either one. But I think it's easier to look at the y value of 0. So I'm getting closer and closer to 0, closer and closer to 0. Oh, and then I stay the same. So you see how from this point to this point, this point to this point, I have the same y value of 0.0037, and then after that second 0.0037, I start going back up. What this means is I need the y value, or I need the t value right between those 2 points. So my t values are 0.112 and 0.113. So my time that my parametric touches the road, touches the x-axis, is right between 0.113 and 0.112. Or in other words, 0.1125. seconds. And we did this by hitting trace and look for lowest y value. Between 0.112 and 0.113. I know it's messy, but that's the only way to find that t, because now normally, like if we were using equations, functions, you could type in y equals 0 and find the intersections. But unfortunately, we only have 4 options for calculate when we're dealing with parametrics, unfortunately. We wish that they would update these calculators so that they would do more, but unfortunately we can't. Are there any questions? All right. So we did